questions. So this is question 1, and I think if you look back in the last few years, you'll see that this, there's a style to this type of question usually. It's usually focused on mechanical vibrations, and you can see there's a picture, figure question 1, down here, which is a mass spring damper, okay? So what it says is an aerospace system modeled using a single degree of freedom oscillator, which is shown in this figure, and it gives you some physical parameters, so some actual numerical values, okay, and it tells you that there's a forcing function applied. It tells you what the magnitude of the forcing is, and so on, okay? So the first part of the question asks you to derive the equation of motion for this system, okay? So let's have a quick look at that. So first, derive equation of motion. You can tell quite a lot by looking at the marks distribution as well, okay? So relatively small amount of marks for A and B, and then quite a lot of marks for this part. Actually, it says D, but this is a typo. It should be C. So you can tell that within this question, there'll be a lot more work in this third part than these first 2 bits, okay? And the structure of these exam questions, I've already said to some of you in conversations in tutorials and so on, is the general structure of questions, at least in this exam, is, everybody should be able to do this first part A. Nearly everybody should be able to do part B, but by the time you get to part C, it's going to feel much harder, okay? And that's kind of, a purposeful way of designing exam questions, so we differentiate out, like, the cohort's ability, if you like. People who can get right through and answer every single thing in a question, there'll be a very small percentage of those people in the overall, when we do the marking, okay? So it should feel like, okay, I've done that, that's reasonable, but now this is getting tough in these later parts of the questions, okay? There's a bit of that also in the overall exam. So in parts A and parts B, generally part A should be a little bit more achievable overall. The questions in part B are slightly harder and slightly longer, okay? But again, they still have this structure so that everybody should be able to do some of the initial parts of the question. So in the solutions online, just have a quick look at the solutions for this. So it says derive the equations of motion. So if you just write it down, you'll get some marks. Okay, so this is the equation of motion that we're looking for, this one that we went and wrote down a lot in the lectures in the early part, mx double dot plus cx dot plus kx equals f. Okay, so you'll get some marks if you write it down, but if you draw the free body diagram and have some explanation of how you've derived this equation, then you'll get all of the marks. Okay, so that's the kind of thing. So if you look at the terminology, if this said write down the governing equation of motion, then you'd get all the marks for writing it down. But if it says derive the governing equation of motion, it means you actually have to show some methodology by which you've arrived at that equation. Okay? So, and that's explained here in my scrawling on the right-hand side. So critical damping ratio. So this is really about plugging in numbers and remembering some of the expressions about the single degree of freedom oscillator. So the critical damping ratio is given by this formula, and we can plug in the numbers to get a value. And again, typically what you're in the marking scheme, obviously we're looking for a value and units to be given as well, okay? So this gives us C critical. We're given C, the actual value of C is in the question. So to get the damping ratio, we divide one by the other, which gives us this value here, okay? And what you're supposed to notice is that because zeta is less than 1, the system is underdamped, okay? And you get a mark for that. It actually asks that in part B of the question. So if we just go back to the question. So part B says work out what the value is and then determine whether the system is underdamped, overdamped, or critically damped, okay? And as you know from what we did in the lectures and in the tutorial sheets, we're nearly always dealing with underdamped systems because they're the ones that have oscillations. Okay, so it would be surprising if it wasn't underdamped, but you know, you never know what's coming up. So you're asked to explicitly state, you know, it's underdamped. Okay, so now we move on to part C. So remember what I said, that you know this will feel harder. 11 marks out of the total is for this part. Okay, so there's quite a lot more work in this, actually working out what's going on. And this part relates to the forced vibration of the system. So in the question, what it says is, it says the oscillator is forced with a frequency omega 62.2 radians per second. Find the maximum steady state displacement of the system and sketch the graph of x of t against time for one full oscillation of the system with initial conditions set to x is 0.02 meters and x dot is 0. Okay? So there's kind of a lot to digest in that, but it's really applying, you know, forced vibration analysis that we did in the class. So you have to work out a few things. You have to work out what the undamped natural frequency is. You have to work out then the damped natural frequency. Okay, you then get a frequency ratio of the value you're given 62.2 in the question, related to the natural frequency that you've worked out, the damped natural frequency, you've just worked that out. That gives you your R value. Okay, so that's your frequency ratio. And then you use this equation for the dynamic magnification factor. Okay, you've got F. So you've got everything here now. You've got F and K from the question. Okay, you've worked out what R is, you've worked out what zeta is, so you can plug all your numbers into this, okay, and get some value out, okay? And that's what you work out here. Okay, so you work out that it's this meters, in this in terms of millimeters. Okay, so now you've got to work out the last part. Okay, so you've been given some initial conditions, so you're you know that your system is a simple cosine wave because your initial velocity is 0. Okay, you can work out the phase from the phase expression, and then you can draw a sketch. Okay, so I've messed around with this because I've drawn it a couple of times. You actually only need to draw this curve here, this black line. Okay, so I've also drawn on some other lines, one of which is the forcing. Okay, but the question doesn't actually ask you for that. Okay, it just asks you to draw this black line here. Okay, so what you're doing is you're sketching a cosine wave which has been slightly shifted. Okay, so it's shifted by a phase. Okay, it starts at 0.2. So again, I've drawn this pretty badly, to be honest, but it's trying to show that this is where it starts, which is 0.2, and it gets to a maximum of 0.26. Okay, which is what we worked out from the steady state dynamic magnification factor. Okay, so that's the idea of that question, and that last part is quite tough, but kind of doable. So question 2, and again, if you look at the pattern in the last few years, question 2 tends to have this kind of style. It tends to give you some pictures and diagrams to look at. Okay? And it tends to ask you questions based on the pictures and the diagrams. So what does it say here? Question 2, it says, data shown in the figures was recorded from some vibration tests with different damping levels. Okay? And then it asks you, what are these things, these symbols? Okay? And you've got to kind of say what they are. Then it says, what's the dynamic magnification factor when the damping zeta is equal to this value? What's the phase at resonance? Okay, and you're given relatively, these are sort of smallish questions with small numbers of marks for that part of the question. And then the second one here, again, it shows you some pictures, and it asks you to work out state what the type of damping is. Okay? And then finally, part C, write down some sources of vibration that commonly occur in aerospace structures. So everybody should be able to do that. These are dead easy marks, aren't they? Right? Okay, so you can write down some answers to that. Okay, so in the solutions, okay, so x over xs is the ratio of dynamic to static displacement, often called the dynamic magnification factor, which we just had in the last question. R equals W omega over omega n, that's the frequency ratio, and this phi symbol is the phase. Okay, so that should be all pretty straightforward. So when zeta is 0.0625, what's the dynamic magnification factor? Well, of course, the curve is the dynamic magnification factor, but what engineers are most interested in is what's the peak value. Okay, so it's when people say what's the dynamic magnification factor, they mean how big could the oscillation get or be magnified. Okay, so the answer is it's 8. Okay, because we don't really care if it's magnified. The input is magnified by 1. We don't really care, but we do really care if it's 8 times bigger than the input. Okay. So, and what's the phase at resonance? Well, of course, resonance. Here's the phase diagram. Resonance occurs at 1 when r is 1, and here it's equal to pi over 2. So these values here are in radians. Unless it states otherwise, phase is always in radians. If it said degrees, then obviously sometimes you get degrees. Then this would be 0, 90, and 180. So this is pi over 2. Or if you give the numerical value of 1.5, whatever, that's fine as well. So next one, it says about these plots. So what's the plots? Well, what you're supposed to notice from this diagram is that this decay is almost like straight lines here. Okay? And this decay is like an exponential decaying envelope. Okay, so the straight line decay is friction damping, and the exponential decay is viscous damping. So that's what the question is looking for. So, and then it asks you. So again, here you get a little bit of, you get 2 marks for each. So if you just wrote it down, you'd get 1 mark. If you explain why you've got it, from the exponential decay curve, from the shape of the decay curve, then you get that extra mark. And then these are typical answers to part C. Okay, so people write down things like this, which are all acceptable. And there's other things that you can come up with for sources of vibration. So that's question 2. So they're basically, both of those questions are basically mechanical vibrations, aren't they? Question 3 is typically a rigid body dynamics question. Okay, and so that's what you've got in this from last year. And it tells you that there's some mechanism that you've got to analyze. It says it's from a helicopter, but it's arbitrary, it doesn't really matter, it's some kind of system. It's giving you the I, J, and K out of the page, so you already know that this is the type of format of the thing you've got to use. And it tells you that this rod here has collars A and B, and it can slide in some sense along these rails. And it asks you to find angular velocity of the rod when the angle here is at a certain point. What's the velocity? So these are sort of 10 marks, and then the last part asks you to find the acceleration, again, when it gives you some data. Okay? So this is going to be one of those questions. So again, looking at the solution, it's quite important to try and draw an accurate diagram and do the trigonometry first, because that's obviously plays a big part in getting these things right. So if there's obvious angles and things on the diagram, then you can work that kind of stuff out, can't you? It helps also, to write down your coordinate system, and if you want to just give yourself a reminder of these kind of relationships, you write those down. But basically we go through the types of thing that we've done in the last part of the course, so working out the velocity at one point based on the velocities at the other points, and then this vector component is replaced with a rotation multiplied by a distance, okay? And I've actually updated, I noticed that I'd written these the wrong way round, okay, compared to how they should be for the convention, so I've actually just, today I've updated the PDF, okay, so these are actually the right way round now. So this is then sort of turning the handle. You know, the distance vector is related to the trigonometry, so you can put all that into an expression and multiply it out to get your components in terms of I and j. You're given the velocity at A, so you can write that down. Again, the velocity at B you can write down as an angle times a distance, so you can multiply all that out. And most of these questions are coming down to, you know, getting to a point where you can equate terms in I and j. So that the format of these questions, the solution to that is, you know, draw the picture, write down the governing equation for velocity or acceleration, plug everything in, and then equate terms in I and j, because they have to equate, and then you pretty much always find that they're a set of simultaneous equations, okay? And so you can solve these as a pair of simultaneous equations, which allows you to get something out. In this case, we were asked to find the angular velocity, omega AB, and so that's what we end up with as our final kind of solution to part A of this question. Part B asks you to work out what the angular velocity of VB is, and now you've worked this out, you can plug that in, and you can leave it in these terms, just in terms of an I component and a j component. All right, so that defines a vector. So the format for part C is exactly the same, but of course, because it's the acceleration expressions, it's a little bit more algebraically intense. So you're asked to find the acceleration, so you write down your acceleration equations. You know some of this stuff already, right, from the previous part of the question, and you're given this acceleration from the question as well. So as I said, it's just a case of trying to plug everything in, equate terms in I and j, and then solve simultaneously. So that's what you're doing down here. And then you can come out with the angular acceleration as your final answer. Okay, so you know, in exams these kind of things are hard to get right because it's easy to make a small mistake, isn't it? Okay, but if you just try and follow the basic format, write the equations, plug it all in, equate I and j, solve simultaneously. So that's section A in the exam, and the pattern in the marking that I see is that most people do very well on question 2, normally the kind of looking at the pictures one. Question A people do pretty well on, and question 1 people do pretty well on, but question 3, you know, because of I think a lot of people find the rigid body stuff harder, lots of people don't do so well on that. The ones that tackle it and know their stuff do just as well as the other questions, but I think in terms of revision, what I noticed, students sometimes think, well, I'll really focus on the first half of the course, maybe I won't revise some of the rigid body stuff because I find it harder. And you see that as a pattern in the marking. So that's part A. So part B, you've got a choice now of two of these questions. You've got 2 questions, you've got to choose one or the other. So obviously you need to have a read through and work out which one you reckon you're going to get the most marks on. Okay, I try and make them relatively even, but again, what you see in the marking is that some people, like some years, almost everybody chooses one of the 2, so that I obviously done something in the other one that they don't like. And some years it's a bit more even, so some years it's a bit more of an even split. And that's usually what I'm trying to aim for, that they're both sort of roughly as hard as each other. So this one, you know, it's typical as well to give a bit more preamble. So this one talks about, you know, that there's a test specimen, testing in a lab. Here's a picture of it down the bottom. Okay, so probably something that you haven't seen before. Okay, some kind of, you know, system that you're being introduced to in the question. And It gives you a whole bunch of parameters. You know, now this time it's telling you that it's a beam. Okay, so it's giving you some beam properties. So that should immediately make you think, well, I'm probably going to have to go to the formula sheet and use the equations for beams from the formula sheet. And probably, you know, it's giving you dimensions and so on. What is it giving you? So, again, you might have to use the equations for second moment of area or those types of things as well, okay? So the first bit is to calculate equivalent stiffness of the beam so that you can model it as a single degree of freedom system. Then this bit here is a thing that can come up. It's basically asking you to, you'll get marks for deriving this equation basically. So it's saying that ignoring the mass on the beam, assuming damping is from a viscous damper, show steady state vertical displacement of the specimen is given by this. Okay, so this is like this is the transmissibility equation, isn't it? Okay, so it's asking you to do the simplest version of the derivation of that. Okay, and then again, same kind of style as the other ones. As we go to the later parts of the question, things are going to get a bit tougher. Okay, so this bit here is asking you to consider what happens when part of a test actuator switched off and then we gather free vibration data. Okay, so you've got to then calculate a few things from that. And then lastly, it asks you to calculate the frequency when x equals y. Okay, so that's actually slightly harder than it looks. Okay, and again, so you're getting some marks for that. So let's have a look at the solution. Excuse me. So as I said, to start off with, it's asking you to find the stiffness. Okay, so you go to the formula sheet. It tells you for a cantilever beam that's the equivalent stiffness is this, and you've got all of these values given to you in the question, so you can plug those in. Okay, first, before you do that, you have to work out what I is, the second moment of area. Okay, so we need 3EI over L cubed. Again, that comes from the formula sheet, and you're given the quantities you need. Okay, so in this case it's a circular beam, you're given the radius. Okay, you can plug that in to get a value for second moment of area. And look, I've been bad there and left the units off, haven't I? That's really bad. I'm going to lose my mark. So when you've got second moment of area, so you can plug it into the K expression and you can get some equivalent stiffness. So, you know, even though this is question in part B, this should be easy marks, right? Because this is basically finding two formulas on the formula sheet and plugging in numbers. And, you know, that shouldn't be difficult. But you've got to recognize what it's asking you to do. And then if the stuff's on the formula sheet, it should be straightforward. Second part is not that straightforward in the same sense, because this is asking you to derive something. Okay, so it's saying, can you derive that expression for transmissibility? So that's obviously a bit tougher, right? Especially if you're not keen on deriving the equations. But if you remember, the transmissibility expression is for when the support input is given. Okay, so the forcing is coming from moving the base in this case. All right, so you can do a free body diagram and write down these initial equations. Okay, and it's the kind of format that we did all over and over again in the first half. You make an assumed solutions that these are sine waves in the forms of exponentials, plug those in, the exponential time dependent bit divides out, so you end up with an x over y. Okay, and then the last little bit is if you divide all the terms by k, so if you divide top and bottom by k basically, you can prove that this thing is what's given in the question, which is this bit here. Okay, so that's kind of a bit of like bookwork derivation. Then in part C, what you're asked to do is a free vibration sub question. Okay, so it gives you some data, and then you're asked to work out estimate what the damping zeta is, and so again, you have to plug in the numbers to that. This bit of the question here is something that you you won't have seen before necessarily. All right, so you've seen it now, but for people who were doing this last year, they won't necessarily have seen it. So this is the type of, so getting to the end of the paper, harder part of the question. So here I'm looking to see who can solve a problem that they necessarily haven't trained themselves for, because it's asking you what's the effective weight of the beam. So if you've got a cantilever beam, you clamp one end into a support and the other end is moving. Not all of the cantilever beam mass is participating in the vibration. Okay, so it's something that's commonly done to take a sort of effective amount of that mass and include that in the vibration. So that said, it should be something that's, you know, doable in an exam. So the way you do it is you work out your natural frequency, so you're given some data on that. Then you can rearrange this natural frequency equation to get an estimate for the mass. Okay, so this is the mass that's participating in the vibration. You know how much the specimen weighs, okay? So you can subtract one from the other to give you, you know, the effective bit of the beam that's taking part in the vibration. That's what it's asking you to find. Okay? So, and then it asks you to do that as a ratio, so you can work out using the volume of the beam, and the density gives you its actual mass, so you've got the ratio of the part of the beam that's participating in the vibration compared to its dead weight, if you like, or its complete mass. And so again, the reason, so if you're on the ball, you'll have recognized that for a cantilever, you know, the bit that's clamped in the end is not participating, but the bit at the other end is. So this is you get a mark for noting that as well. So again, we get to this is the last part of a question at the end. So this is deliberately set to be quite difficult. So you kind of really have to know this from the notes. And so if you go back to the notes for transmissibility, there was a little tiny bit where we showed that when x equals y, then this is equal to 1. This thing here is equal to 1. So you can square both sides, you can multiply through and find this relationship. And if you do that, you can work out that either r is 0 or r is root 2. Okay, and so omega over omega n is r. So we have this relationship is equal to root 2. We know what omega n is because we've got the data for that. So you can plug that in and get a final value. Okay, so this is deliberately quite tricky. And as I say, when you're marking it, only a few people will get right through these kind of longer questions and kind of come out with all of these, everything right. So last question on last year's paper. So this one was basically encapsulated what we did last lecture. So it shows you a picture of an aeroplane. Okay, and the question gives you some data that it's a single prop plane with a rotational speed given there, and gives you some data about the moment of inertia of the propeller and the rotating shaft. Okay, so then part A is a gyroscope question. Okay, so it says it's traveling at 400 kilometers an hour, turns left on a radius of 500 meters around J-axis. And it actually gives you the I, J, and K axis in the picture down here, look. Okay, so it's giving you the I, J, and K. And you're asked to find out, you know, how the gyroscopic moment affects the aeroplane, and does the tail rise or fall. Okay, so quite, in some ways tricky, but also it's just, if you know the gyroscope equations, it's a straightforward application of that. Part B is what we did on balancing. So this is a tabular balancing-ish question. And what it tells you is that the propeller and shaft and engine have some unbalanced masses in them. Okay, so they're like a rotating shaft. So the prop shaft goes right through into the engine. And this table is partially completed, and it tells you some of the information you need to know about this system. Okay, and then it tells you to take moments about plane B, which is this one here, where one of the bearings is, complete the table so that you get static and dynamic balance, and then it tells you to show the working in the answer book and so on. And then the final part of the question is, again, what we did in the example last time, is tells you to find out the forces acting on the bearings in the system due to the unbalanced masses. Okay, so this is all about either gyroscopes or balancing this question. So if you don't like those things, then you wouldn't choose this one, I guess. So, solution. So to start with, we have to take some of the information from the question and work out some key components. So we have to work out what the speed of the aircraft is. We have to basically convert these things into appropriate units for us. Okay, so the first one is 400 kilometers an hour is 111.1 meters per second. We write down the gyroscopic equation. Okay, we note that this is what's given in the question. Okay, we need to work out what the omega value is. Okay, and we do that from V over R, so the arc length approximation, to give us a value times J. We've got the speed of the engine given to us, the RPMs, so again we convert that to a radians per second times K. Okay, and then we can plug that into the equation for our gyroscopic moment. We get the moment value. Okay, and then if you've done the questions in the tutorial sheet, you'll know that the thing that's a bit non-intuitive is that if the moment's acting this way, the reaction is in the opposite direction. Okay, so you have to think about if the moment's acting in positive direction, the reaction's the other way, and so you have to work out whether the nose goes up or down or the tail goes up and down. Okay, so you can give a solution to that. And then the next two parts are very similar to the example we went through last time. So this is my table for the bearing balancing problem. Okay, so what I did was first of all I wrote down what I was given in the exam question, and then these ones in red boxes are what I've worked out from doing the working below. Okay, so the working below follows exactly the same pattern as we did in our previous example. Okay, so first you work out these ones, the MRD ones. Okay, so you go through and work those ones out first, and again this is just a case of cranking out these equations and being very careful when you're working out the arctan, as I said to you last time. Okay, you need to think about that. And then you go through and do the sum of MR. So again, you go through all of these sine and cos relationships and carefully work out the arctan, work out what the MR value is, and that you put those back in here. Okay, so then you can work out all of the data for these missing entries. Okay, just one thing to note is it doesn't give it in the question. It tells you that all of these things are 0.2 meters apart, and it tells you to take moments about point B. Okay, so this one is minus 0.2. Okay, so do you see what I mean? B is not at the end. So this is the propeller, this is the bearing, these are two unbalanced planes, and then this is another bearing. Okay, so when you're doing distances, these aren't filled in for you, but you can start at 0 and you can go positive one way and you can go negative the other way. Okay, so that's just a minor detail to note. So you fill in the table, and then the last part is the bearing loads. Again, this is exactly what we were looking at in that example in the last lecture. The magnitude is mr omega squared, and you given omega squared given omega in the question in part A. You're given the MR values of what you've worked out in the tables, so you can plug those in and come out with solutions for loads on the bearings at angles. Okay, so that's quite a rapid run through the solutions, but what you see is that those questions in the second part can encompass a combination of mechanical vibrations plus rigid body dynamics as well, can't you? Whereas in part A, they tend to be either mechanical vibrations or rigid body dynamics. So in those questions in the second part, it can become more complicated. Has anyone got any questions?